Up to this point, we've talked about the different turbulence models that are available in Fluent. The next topic is near wall treatments, and what we do about turbulence near the wall is equally as important as what turbulence model we choose. A brief discussion of the structure that's found in near wall flows is a good starting point for this topic. In the graphic, you can see the velocity profile in the boundary layer. The boundary layer thickness delta is the location at which the velocity reaches 99% of the free stream value. The boundary layer consists of an inner layer and an outer layer. The inner layer also consists of regions. So we have A, the viscous sublayer, where viscous effects dominate momentum transport, and the buffer layer, where turbulent effects become increasingly important, and B, the fully turbulent region, or log layer, where turbulence is the dominant mechanism for momentum transport. This is indicated by the representative velocity signal on the right-hand side of the slide. In the log layer, there's continuous fluctuation, whereas in the viscous sublayer, the fluctuations are sporadic. In the outer layer, there's periods of turbulence and periods of inviscid flow. The percentage of time that the flow at a given point in the outer layer is turbulent is called intermittency. Looking more closely at turbulence near the wall, we know that near to the wall, the gradients are high and the velocity changes quite rapidly, and the velocity profile versus wall distance might look something like this. If we take the same graph again, and we make the y-axis, the x-axis, have a logarithmic scale, and we normalize the velocity using a quantity called the friction velocity, or u tau, which you can see is defined as the square root of the wall shear stress divided by the density, and we also make the wall distance y dimensionless using the friction velocity, the physical wall distance, and the viscosity of the fluid, then we arrive at the graph on the next page, which shows that the shape of the velocity profile using this normalization is generally the same for all flows. As the previous slide hinted, if we scale the variables near the wall, then the velocity profile takes on a predictable form where it transitions from linear behavior very close to the wall to logarithmic behavior slightly further away from the wall, although physically still very close to the wall. The logarithmic velocity profile appears as a straight line on this plot because a log scale is used for the x-axis. By using the non-dimensional velocity and non-dimensional wall distance, we see that there's predictable boundary layer profiles for a wide range of flows. And this is shown on the graph here, where we have velocity profiles from two different flows plotted on the same graph. One of the flows at a lower Reynolds number, and the other flow at a higher Reynolds number. You can see that close enough to the wall, the profiles are identical. Further away from the wall, in the outer part of the boundary layer, then the profiles begin to deviate from the logarithmic profile. As we see on the plot, for higher Reynolds number, the logarithmic region extends further to the right on the x-axis. If we had an even higher Reynolds number, then we'd expect it to extend even further to the right. Because near-wall conditions are often predictable like this, then functions can be used to determine the near-wall profiles instead of using a very fine mesh that actually resolves them. The functions that do this are called wall functions. Two different strategies are available for dealing with the near-wall region where solution gradients are very high. Accurate calculations here can be critical to the success of the simulation. The two strategies are either to resolve the viscous sublayer with the mesh or to use a wall function. If the viscous sublayer resolving strategy is selected, the distance of the first grid point from the wall should correspond to a y plus value of about 1, and as you can guess, this can add significantly to the mesh count. A low Reynolds number turbulence model, like one of the k-omega models, should be used. When we say low Reynolds number turbulence model, we're not talking about the Reynolds number of the flow or the system Reynolds number. Instead, we're just referring to the fact that the model equations can be solved on a grid that penetrates into the viscous sublayer without having to modify any of the terms in the equations. Generally, if forces on the wall are the most important thing in the calculation, and this can be if we're interested in predicting skin friction, turbomachinery blade performance, flow separation, heat transfer, then the viscous sublayer resolving approach would be the preferred approach. If you elect to use wall functions, then the first grid cell should be located in the logarithmic layer that we saw on the previous slide. In many cases, this means that the y plus value of the cell should be between 30 and 300. It's important to point out, though, that this is not an absolute guideline for the y plus value. If the system Reynolds number is very high, then the log layer can extend to values far past 300, and that means that in cases such as that, higher values for y plus can be tolerated if you're using wall functions. On the other hand, if the system Reynolds number is on the low side for a turbulent flow, the log layer might only extend out to 50 or 100, and then if you put the first grid point at y plus equals 30, there would only be 3 grid points in the boundary layer, and that would also not be sufficient. Wall functions would typically be used with high Reynolds number turbulence models like the K-epsilon models or the Reynolds stress models. And again, by high Reynolds number turbulence model, we simply mean that the model equations cannot be solved in the viscous sublayer without some kind of modification. It doesn't have anything to do with the Reynolds number of the flow or the system Reynolds number. If you're more interested in what's taking place away from the wall than you are in the forces on the wall, then wall functions would probably be the approach that you would take. On this slide, we can see how the choice of near-wall modeling strategy affects the mesh distribution. In a relative way, the mesh on the left represents a mesh that would be used for wall functions, and the mesh on the right represents a mesh that would be used with a viscous sublayer resolving strategy. So if wall functions are used, then fewer cells are required in the mesh. The meshes that we see here should only be considered to be for illustrative purposes, because if the red part of the curve indicates the boundary layer, you would typically need to have many more cells than 2 to 3 cells throughout the boundary layer to have a good solution. One thing to mention about the picture on the right is if you remember the previous slide where there's a statement that the first grid point should be at y plus equals 1, the reason for that is not because y plus equals 1 is a magic number. The reason is that if you have the first grid point at y plus equals 1, and a moderate grid expansion ratio is used, so the size of the cells doesn't increase too quickly as you move away from the wall, then the result will be that the mesh that you have will be suitable for resolving the very high gradients that are found inside of the viscous sublayer.